Welcome to Deming's funnel experiment. In this video, we will explore why tampering with stable processes often leads to worse outcomes, and how Deming's work demonstrates the importance of understanding process variation. Well-intentioned adjustments to stable processes usually create more variation than they eliminate, sometimes doubling or even infinitely increasing it. Deming's funnel experiment shows how managers, by tampering without understanding the causes of variation, can worsen performance. The experiment uncovers a counterintuitive truth. Leaving a stable process alone yields better results than constant adjustment. Tampering, as Deming described, occurs when reactions to normal variation create instability. Common examples include adjusting quotas based on current outputs, changing policies after single survey results, or reacting to budget variances. Understanding the difference between common cause and special cause variation is essential. The funnel experiment uses basic equipment to model how management decisions affect process stability. A funnel is placed above a target on paper, and marbles are dropped to see where they land. The goal is to get each marble as close to the target as possible, simulating real-world efforts to hit specifications. Even when the funnel remains stationary, natural variation causes marbles to land differently, representing inherent process variation. The experiment tests 4 rules for adjusting the funnel, each reflecting common management responses to variation. Rule 1. No adjustments are made regardless of where marbles land. The funnel remains aimed at the target. This produces the lowest variation and best results, with marbles forming a predictable pattern around the target. The distribution shows a stable process where all variation is due to common causes. Rule 1 is the control baseline, proving that a stable process works best when left undisturbed. Rule 2. After each drop, measure deviation and move the funnel the opposite distance to correct for error. Though it seems logical, this doubles variation compared to Rule 1. The feedback loop amplifies natural variation, making the process more unstable. Operators who adjust machines after each measurement inadvertently increase instability. Rule 3. Set the funnel an equal distance in the opposite direction of the error from the original bullseye. The reference point is a fixed standard, which appears rational. However, the process becomes increasingly unstable, with variation growing exponentially. Examples include changing policies based on the latest surveys or modifying targets after every result. Rule 4. Position the funnel above where the previous marble landed, making the last result the new target. This creates a random walk pattern, with the process drifting away from the original target. The last event becomes the new standard, mirroring management using recent performance for future expectations. Examples include using budget variances to set new budgets, losing connection to original goals. Comparing the 4 rules, Rule 1 consistently delivers the best results with least variation. Rule 2 doubles variation, Rule 3 causes exponential instability, and Rule 4 results in a random walk with mounting deviation. All adjustment rules are forms of tampering, where well-meant corrections actually worsen the process. Like quicksand, persistent adjustment accelerates decline. Variation is categorized as common cause or special cause. Common cause variation is inherent to the system, resulting from many random factors, and is predictable in aggregate. Adjusting for common cause variation increases overall variation, as shown in Rules 2, 3, and 4. Special cause variation comes from external assignable factors and can be identified and eliminated. Actions to reduce special cause variation differ entirely from those required for common cause. Adjustments should be made only for special causes, not for common cause variation, which needs fundamental redesign. Tampering happens in manufacturing, business management, and performance management. Adjusting machine settings after every moisture measurement in rotary dryers, operators changing controls based on single sample results, or equipment adjustments to normal variation all increase variability. Changing policies after employee surveys, modifying sales quotas to match current output, or using budget variances to set budgets are forms of tampering. Rewarding or punishing workers for outcomes determined by the system, ranking employees when differences are within natural variation, and implementing corrective actions for stable process results are additional examples. Tampering increases variation, wastes adjustment efforts, and damages employee morale and trust. Managers who blame workers for system-determined outcomes cause morale to suffer, as employees see the futility. Good intentions directed at the wrong problems leave organizations worse off. Tampering prevents quality improvement by increasing variation and moving processes away from their stable state. Control charts are vital for distinguishing signals from noise in process data. Plot process results and time sequence, establish control limits, monitor for points outside limits, and investigate signals for special causes. If the process is in control, pursue improvement through fundamental changes, not tampering. Changes without control charts often lead to tampering and instability. The distinction between statistical control and out-of-control states is crucial, as improvement actions differ. A process in control is ready for fundamental improvement, not adjustments based on individual results. Stop tampering. It's not improvement. Begin improving by recognizing harmful reactions to common cause variation. Use statistical methods to determine when special causes need investigation. Punishing or rewarding for system-driven results wastes effort. Fundamental change comes from better materials, equipment, training, or methods. Reduce inherent variation through root cause analysis. Use control charts and statistical thinking to genuinely reduce variation. Knowledge prevents well-intentioned destruction. Natural variation is normal, and every stable process has inherent variation that can't be eliminated by adjustments or effort alone. Logical adjustments often backfire, as common sense reactions ignore statistical properties. Persistent efforts without knowledge can destroy everything. System thinking outperforms individual metrics, as focusing on workers rather than the work system misdirects improvement. Statistical methods are essential management tools for effective decision-making and leadership. Implement control charts to monitor key processes and distinguish common from special causes. Train managers and workers in statistical thinking and principles of variation. Focus improvement efforts on systems, not individuals. Investigate root causes when special causes appear, and redesign for quality through changes in materials, methods, equipment, and training. Apply funnel principles by identifying areas of tampering, establishing process control, and building organizational capability in quality methods. Shift from managing results to managing methods, focusing on processes that create outcomes,